We need to take a new look at gravity. And so let's take a look at Newton's law of gravitation. Let's look at the old way. And there's nothing really wrong with the old view of gravity. We would say that the force of gravity was equal to mg. It described we took a ball and we would drop it. And in the absence of drag force, we would say that the ball then would accelerate towards the earth at a value of little g, which we knew was something really close to 9.8 meters per second squared, which meant that the object would increase its velocity by 9.8 meters per second every second. And there's really nothing wrong with that. Describing this as mg is totally fine when we're talking about reasonable heights, building heights, dropping it from the table, dropping it in any sort of classroom setting. But the new way we need to look at it is if we're talking about launching satellites, or we're going all the way to the top of some mountain and we really want to look at gravity in a precise way. Well, it turns out that Newton describes gravity as F equals G mm over r squared. This capital G is a universal gravitational constant, 6.67 times 10 to the negative 11th. Remember, that's a really small number. M and M are just the two masses. You could label it capital M and little m, or M1 and M2. I usually go with capital M and little m because we're typically talking about a planet and then the mass of something else, the mass of you, the mass of a book, the mass of a box, or the mass even of a satellite. And then R, I know we think of it as the radius, but it really is just the distance between the two masses. The distance between the masses. Okay? And most people would refer to this type of relationship as an inverse square law. If you take a look at how the force is a function of r, the force is proportional to 1 over r squared, right? Which says that, like, if you double the distance, you cut the force into 1/4. Okay, and it's an inverse square law. Okay, and you're like, well, how are these things then related? I mean, if this still is accurate, as long as our heights aren't very big, how are these things the same? Well, if you look at this term right here, that makes up little g. And so if you plug in capital G, which is 6.67 times 10 to the negative 11, and you plug in the mass of the Earth and the radius of the Earth, this will be pretty much little g. And let's look at the radius of the Earth is something like 6.37 times 10 to the 6th meters, right? That's like 6.37 million meters. And then the mass of the Earth is something like 5.97 times 10 to the 24th kilograms. So feel free to plug in g, plug in the mass of the Earth, and plug in the radius of the Earth squared, and that will end up being something like 9.8 meters per second squared. And as long as we're not changing our distance, so we're standing on Earth, and we're talking about any object, then we're talking about an object here, and then the Earth we consider all at the center. Then the radius is this distance. And that radius, as long as we're not too far from the Earth's surface, that radius is always just the radius of the Earth. And so no matter where we go on the Earth, we're still at the acceleration of 9.8 because this factor here is just what little g is. And then if we keep varying different masses, then we get different weights, which is why your typical weight is proportional to your mass. The question becomes, well, what if I go off the Earth's surface? Well, then we can take this formula and you can think about as far as what it becomes. F becomes G, M, M, and then your R really is the radius of the Earth plus H. And again, now we're talking about you being way over here. And so this is your little r, that would be the radius of the Earth, and then that being how high you are off the Earth's surface. And once H becomes big enough, certainly big relative to the radius of the Earth, then this whole factor turns into something that's not 9.8 meters per second anymore. Okay? Now, old school, we're throwing a baseball, we're throwing a basketball, we're hitting a golf ball. h is going to be completely insignificant, which is why we can go old school. Now, if we start launching a satellite, or we have something orbiting, then we're going to have a significant h, and then the force of gravity is no longer going to be what it used to be. Our little g changes. If you think about here, and then what if we climb to the very top of Mount Everest? Mount Everest is something like 8,800 meters above sea level. Again, gravity down here is 9.8 meters per second squared. Little g up there, the acceleration due to gravity based on the fact that it's changing, is something of the order 9.77 meters per second squared. So things would fall to the earth ever so slightly slower if you're on top of the mountain, and then obviously go further and further and further away, and then it keeps changing. Okay, so this is the idea of we have a new force, but it does correlate to the old force given if h is small enough.